तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. We shall be covering today the 5th lecture of the first module on Introduction, Prestressing Systems and Material Properties. In this lecture, we shall first cover the constituents of concrete, aggregate, cement, water, admixtures, and then we shall cover the properties of hardened concrete, strength of concrete, stiffness of concrete, durability of concrete, high performance concrete, and the allowable stresses in concrete. Constituents of concrete. The concrete is a composite material composed of gravels, which are the coarse aggregates, sand, which are the fine aggregates, and hydrated cement, which is the binder. Now, it is expected that the student of this course is familiar with the basics of concrete technology. Only the information pertinent to prestressed concrete design is presented here. All of you should have undergone a course in concrete technology, which you have also used in reinforced concrete design. Hence, these discussions of today will be more a review in nature rather than going into the details. This is a petrographic section of hardened concrete, and you can see that the concrete itself is a composite material consisting of this large coarse aggregates, and in the space between the coarse aggregates is filled up by the fine aggregates and the hydrated cement paste. Although the concrete is a heterogeneous material, it is treated as a statistically homogeneous material for the purpose of design. Now, the first constituent, the coarse aggregates, these are granular materials obtained from rocks and crushed stones. They may also be obtained from synthetic materials like slag, shale, fly ash, and expanded clay for use in lightweight concrete. Now, the coarse aggregates is the basic constituent of the concrete because it covers the maximum volume within the concrete. The next constituent is the fine aggregates. The sand obtained from river beds or quarries is used as fine aggregate. Now, the fine aggregate along with the cement paste fill the space between the coarse aggregates. Now, the important properties of aggregates are the shape and texture, size gradation, moisture content, specific gravity, unit weight, durability, and absence of deleterious materials. Most of these properties are covered in details in a course on concrete technology. There are some requirements of aggregate in the code in section 4.2 of IS 1343. Now, the code allows us to use aggregates within a nominal maximum size. The nominal maximum coarse aggregate size is limited by the lowest of the following quantities. First, it is a quarter of the minimum thickness of the member. Second, the spacing between the cables or strand minus 5 millimeters, and third, 40 millimeters. The purpose of restricting the maximum aggregate size is that the concrete should be able to flow properly within the member during the casting. If the concrete is not able to flow properly, then it creates honeycombs, and as you remember that the prestressed concrete is subjected to stresses even before the service loads acts on it. If there is honeycomb, if the quality of concrete is not good, then the prestressed member will not be able to sustain the prestress itself. Now the code says that the coarse aggregate should be free of deleterious substances like clay lumps, wood, coal, shirt, silt, rock dust, and organic materials, some unsound and friable particles. Now this type of materials reduces the bond between the coarse aggregate and the cement paste. They may also lead to the corrosion of steel if those deleterious materials are corrosive in nature. The third constituent of concrete is the cement. Now in present day concrete, the cement is a mixture of limestone and clay heated in a kiln to 1400 to 1600 degrees Celsius. The manufacturing of cement itself is a subject by itself, and it is one of the important inventions of the development of reinforced concrete. Now the types of cement that is permitted by the code 1343 for prestressed applications are the following. This is given in clause 4.1. The most common type of cement is the ordinary Portland cement, which should conform to IS 269. The second type is the Portland slag cement, conforming to IS 455, but with not more than 50% slag content. Slag is a byproduct of the steel construction. This is used in the manufacturing of cement, and that type of cement is called Portland slag cement. The third type of cement is the rapid hardening Portland cement, conforming to IS 8041. If there is pressure in the work schedule of producing prestressed members quickly, then the rapid hardening cement can be used, which gains strength quickly and the prestress can be transferred earlier. The fourth type of cement which is allowed is the high strength ordinary Portland cement, conforming to IS 8112. This type of cement gains high strength, which gives higher strength concrete. Now the three constituents, the coarse aggregates, fine aggregates, cement, are mixed in a rotating drum, and then water is added. The water should satisfy the requirements of section 5.4 or of IS 456-2000. The code clearly states that the water used for mixing and curing shall be clean and free from injurious amounts of oils, acids, alkalis, salts, sugar, organic materials, or other substances that may be deleterious to concrete and steel. The potable water is accepted for constructing concrete. Again, the bottom line is that there should not be any deleterious material which may reduce the bond and the hydration of the cement, and also which may affect the corrosion of the steel reinforcement. In addition to these four constituents, some admixtures may be added to concrete. The 1343 allows to use admixtures that conform to IS 9103. Now the admixtures are broadly classified under two groups. The first group is the chemical admixtures. Now the different types of chemical admixtures are air entraining admixture, which helps to have small air bubbles inside the concrete. The second is water reducing admixture, which helps to reduce the water, maintaining the slump of the green concrete. The third is the set retarding admixtures. This is used to elongate the setting time of the concrete. The fourth is the set accelerating admixture, which accelerates the setting of the concrete. The fifth is a combination of the earlier two types of admixtures, that water reducing and set retarding admixture. And the sixth is water reducing and set accelerating admixtures. Now, these admixtures are selected based on the specific need of the structure and the construction. Usually, catalogs are available with the suppliers of these admixtures, and specifications of how to use them and what is the dosage of these admixtures are provided in these catalogs. Now, those catalogs should be maintained while manufacturing the concrete. The other type of admixtures is the mineral admixture. The mineral admixtures can be cementitious and pozzolanic material. Example is fly ash, that this type of admixtures are used to have some more cementitious material other than the cement, and it is a use of an industrial byproduct. Next, we are moving on to the properties of hardened concrete. So, in this course we are not covering the properties of green concrete because it is expected that the students are familiar with those properties. It is the properties of hardened concrete that influence the strength and the performance of a prestressed concrete member. The concrete in prestressed applications has to be of good quality. This is a very important statement because in prestressed concrete, the concrete is subjected to compression from the transfer of prestress. The concrete requires the following properties. First, the high strength with low water to cement ratio. This is the primary requirement of concrete in prestressed structures, that it has to be of high strength. That is why the code has a limitation on the minimum strength of the concrete, which we shall come to later. The second is the durability with low permeability, minimum cement content, and proper mixing, compaction and curing. At present, durability of concrete is being emphasized. It is being seen that the constructed structures are aging, and repairing and rehabilitating those structures are very costly. Hence, importance is given to the durability of concrete, and the durability involves some properties, out of which the low permeability is the most important. If the concrete has low permeability, then the ingress of water can be checked. The third property of concrete that is required in prestressed applications is the minimum shrinkage and creep by limiting the cement content. We learned earlier that there is a loss of prestress over time due to the compression of the concrete due to shrinkage and creep. Now, we have to have concrete which has less shrinkage and creep so as to reduce the loss in the prestress. Now, the following sections describes the properties of hardened concrete with reference to IS 1343. The strength of concrete is required to calculate the strength of the members. For prestressed concrete applications, high strength concrete is required for the following reasons. See, out of the properties of concrete that we need in prestressed concrete analysis and design is the strength is the foremost property that we need. Now, we need high strength concrete for the following reasons. First, to sustain the high stresses at anchorage regions. Last time we saw that the concrete which is just adjacent to the anchorage block, that is subjected to high stress concentration. In order to sustain that high stresses, we need high strength concrete. The second reason is to have high resistance in compression, tension, shear and bond. The forces in prestressed concrete can be substantially high, and for that we need high strength concrete. The third reason is to have higher stiffness for reduced deflection. Usually high strength concrete has also higher stiffness, and which means we shall have lower deflection in the members. And finally, a concrete which is subjected to less shrinkage will have reduced shrinkage cracks. The shrinkage cracks occur due to the restraint of the shrinkage. Since the restraints cannot be avoided, it is always advisable to have minimum shrinkage concrete so as to reduce the cracking due to shrinkage. Now, how do we quantify the strength of concrete? As we all know that the strength of concrete increases with time, most of the gain in strength occurs in the first 4 weeks, and gradually the gain tapers off. Now, the compressive strength of concrete is given in terms of the characteristic strength of 150 millimeter size cubes tested at 28 days. Now, this strength, which is a standardized measure of the compressive strength of concrete, is called the characteristic strength, and this is denoted as F with subscript Ck. Now, the characteristic strength is defined as the strength of the concrete below which not more than 5% of the test results are expected to fall. This concept assumes a normal distribution of the strengths of the samples of concrete. This sketch will help you to understand the meaning of the characteristic strength. If we sample several cubes, then it is expected that the strength of the cubes will fall into a normal distribution curve. On the horizontal axis, we are plotting the 28-day cube compressive strength. On the vertical axis, we are plotting the frequency or the number of samples for a given particular strength. Now, the mean of this distribution is called the mean compressive strength, which is denoted at FCM. Now, the characteristic strength is defined as that value below which only 5% of the tests will fall. This characteristic strength is lower than the mean strength by a value of 1.65 times the standard deviation of this distribution. Now, instead of going into the details, the code gives us some simple guidelines for sampling and testing concrete. These guidelines are given in the section 15 of IS 1343. Now, based on the strength of concrete, concrete is divided into several grades. Now, the grades of concrete are given in table 1 of the code. Now, the minimum grades that the code allows for prestressed concrete applications are 30 megapascal for post-tension concrete and 40 megapascal for pre-tension concrete. As we had seen while understanding pre-tension members, is that in the pre-tension members there is an obligation of applying the pre-stress at an early edge so as to remove the specimens from the pre-stressing bed. Since the pre-stress is applied at a relatively earlier age, the code specifies a higher minimum strength for a pre-tension members. Whereas for a post-tension member, usually the transfer of pre-stress is after substantial amount of curing and hardening, and hence the code allows us a lower minimum strength for post-tension members. The code also gives us a maximum limit of the grade of concrete, that is 60 megapascal. Now, this provision of maximum grade was because that when the code was written in 1980, the properties of high strength concrete was not adequately documented, and hence this limit was imposed. But over this 2.5 decades, the high strength concrete has been studied, and it is expected that high strength concrete may be used for pre-stressed applications. After proper testing, we have to be careful that the high strength concrete should meet the minimum requirements for pre-stressed applications. It should not have high shrinkage, the heat of hydration should not be excessive, and also it should not be brittle. If a high strength concrete satisfies these requirements, then it can be used for the pre-stressed applications. Now, in the code, there is a provision of the increase in strength with age, but this provision is not observed in the present day concrete, because in the present day concrete the cement gains strength early and it does not increase in strength much beyond 28 days. Hence, this age factor, which is given in clause 5.2.1 in the code, should not be used. In fact, this age factor has been removed from the latest version of IS 456. Next, we are coming to the tensile strength of concrete. Now, the tensile strength of concrete can be expressed by either the flexural tensile strength or the splitting tensile strength. The flexural tensile strength is measured by testing beams under 2-point loading. Sometimes the 2-point loading is also called as a 4-point loading by considering the reactions. Now, this is a simple test where the beam is subjected to a uniform moment over a certain region. Let me explain this by a sketch. In a 2-point loading, a simply supported beam is subjected to equal loads in the middle such that the bending moment is constant over the central region. Now, as the load is increased for a plain concrete beam, there will be a crack at a certain location in that middle third region, and the load corresponding to the initiation of the crack will give us the maximum stress that is occurring at the bottom, and that value is called the flexural tensile strength. The second type of test that is used is the splitting tensile strength. In a splitting tensile strength, a cylinder is laid horizontally and it is applied with a vertical load through its meridian, and at a certain time after the load is increased, it splits along the vertical direction, and the load corresponding to this splitting gives the splitting tensile strength. Now, both these tests are covered in details in the concrete technology course. Hopefully, you should be aware of both these tests. Now, these two tests, the flexural tensile strength and the splitting tensile strength tests, are easy to perform. There is a third type of test for calculating the tensile strength of concrete, that is the direct tensile strength tests. Now, these tests are more difficult to perform, but still they are done for research purposes. Now, what the court says that in absence of any test results, we can estimate the flexural tensile strength from the compressive strength by this following equation. The compressive strength is a more common test for concrete. If we are not able to perform any one of the tensile strengths, then the flexural tensile strength, which we need most of the time in our calculations, can be calculated by this expression. FCR is the flexural tensile strength expressed in Newton per millimeter square. This is given as 0.7 times root over FCK, where FCK is the characteristic compressive strength in Newton per millimeter square. Next, we are moving on to the stiffness of concrete. Now, the stiffness of concrete is required to estimate the deflection of members. We expect that the prestressed concrete members should have reduced deflections because of the upward thrust due to a curved profile, but there may be situations that since the prestressed concrete member is slender, the deflections can be of a concern, and at that time deflections are calculated specifically, and we need the stiffness of concrete to estimate these deflections. The stiffness is given by the modulus of elasticity. For a linear stress versus strain behavior of concrete, the modulus can be initial, tangential, or secant. Let me explain these three types of modulus by the stress strain curve of a cylinder under compression. Since the stress strain curve of concrete under compression is nonlinear, we can define three modulus for this stress strain curve. The first one is the initial tangent modulus, which is also called in short the initial modulus. The second one is a secant modulus for a particular level of stress, where we draw a line from the origin to that particular point in the stress strain curve. And the third is the tangent modulus, where we draw a tangent to the stress strain curve at a particular level of stress. Now, these are the three types of modulus which can be defined for a nonlinear stress strain curve of concrete. IS 1343 recommends a secant modulus at a stress level of about 0.3 FCK. The modulus is expressed in terms of the characteristic compressive strength and not the design compressive strength. I will explain this statement later, but let us try to understand the definition of the modulus of concrete as defined by the code. For a cylinder, when we test under compressive stress, we get this nonlinear stress strain curve. Then the modulus of concrete as per the code is defined for a stress level of 0.3 FCK, and it is in fact a secant modulus of the stress strain curve. Now, this modulus is expressed in terms of the characteristic strength by this expression, that EC is equal to 5000 root FCK, where EC is the short term static modulus of elasticity and FCK is the characteristic compressive strength, both in Newton per millimeter square. Now, remember that here we are using the characteristic strength. We do not use any material safety factor for the strength in order to calculate the stiffness, and this stiffness is the short term stiffness. That means it does not consider any effect due to creep. Now, this expression is an updated expression from IS 456-2000. When 1343 was published in 1980, an older form of this equation is used, but it is expected that in a newer version of 1343, the expression will be same as that in IS 456-2000. Next, we are moving on to the durability of concrete. Now, the durability of concrete is of vital importance regarding the life cycle cost of a structure. The life cycle cost includes not only the initial cost of the materials and labor, but also the cost of maintenance and repair. As I had said before, that at present more emphasis is being laid on durability of concrete, because since the aging structures is a problem to repair and to rehabilitate, we wish that the concrete should be durable enough to have less cost in the maintenance and repair. Now, in the recent years, emphasis has been laid in the durability issues, and this is reflected in the enhanced section on durability in IS 456-2000. It is also expected that the revised version of IS 1343 will have similar importance on durability. Now, the durability of concrete is defined as its ability to resist weathering action, chemical attack, abrasion, or any other process of deterioration. Now, the common durability problems in concrete are as follows. The first one is the sulfate and other chemical attacks of concrete. The second one is the alkali aggregate reaction, that if the aggregates are reactive with the alkaline environment, then it will lead to the reduction in strength of the concrete. The third is the freezing and thawing damage in cold regions. In the cold regions, if water percolates within the concrete and if it freezes, then it creates a tensile stress within the concrete. And fourth, which is a very important durability problem, is the corrosion of steel bars or tendons. In prestressed concrete as compared to reinforced concrete, the amount of steel required is much less. Now, if the steel undergoes corrosion, then the problem in prestressed concrete is even more than reinforced concrete. The reduction in diameter of a prestressing tendon is much higher in percentage compared to the reduction in diameter in reinforced concrete reinforcement. Now, the durability of concrete is intrinsically related to its water tightness or permeability. See, there is a difference between permeability and porosity. The permeability means when there are connected water paths within the concrete, then water can ingress in the concrete and cause durability problems. That is why in order to enhance the durability of concrete, we need water tightness or low permeability. And also there should be adequate cover to the reinforcing bars. If we have adequate cover, then it is expected that there will be less paths of water to come to the reinforcement. Now, to ensure durability, the selection of materials and good quality control are essential. Now, in 1343, the durability is addressed in section 7. Now, again I am repeating that the section on durability in 1343 is much smaller than compared to the section in IS 456. It is expected that in a newer version of 1343, more emphasis will be given on durability. Now, in Appendix A of 1343, there are guidelines on the maximum water to cement ratio and the minimum cement content. The values in Table 9 are for different types of exposure. Now, in this lecture, we are just giving you some sample values from the table. The values for moderate exposure conditions are given below. That means the minimum cement content should be 300 kg per meter cube of concrete. The maximum water to cement ratio should be 0.5. The more cement we have, the better quality of concrete we can expect. And if we reduce the water cement ratio, then we expect that the strength to be high. The table 10 of the code provides values for concrete exposed to sulfate attack. That means this is a special table which is required if we suspect that the concrete can be exposed to sulfate attack. We cannot increase the cement content without a limit, because if we have very high cement content, then the chances of shrinkage and creep also increases. To limit the creep and shrinkage, IS 1343 specifies a maximum cement content of 530 kg per meter cube. Thus, under moderate conditions, the range of cement content is from 300 to 530 kg per meter cube of concrete. Now, let us discuss in short the high performance concrete. With the advancement in concrete technology, the high performance concrete is becoming popular. Especially for prestressed concrete, high performance concrete can be used. Now, what are the attributes of high strength concrete? The attributes are, first, it should be of high strength. As I said before, that the primary requirement of concrete in prestressed applications is that the concrete should be of high strength. Then the second criteria is the minimum shrinkage and creep. The third is high durability. The fourth is easy to cast, and fifth, that it should be cost effective. Now, traditionally, high performance concrete implied high strength concrete with higher cement content and low water to cement ratio. But there is a problem if we use higher cement concrete. With higher cement concrete, it leads to autogenous and plastic shrinkage cracking and thermal cracking. That means, if we are increasing the cement content in order to gain high strength, then it may lead to higher shrinkage cracking, and also it may lead to higher thermal cracking if the concrete is subjected to the diurnal temperature variation. That itself creates another durability problem. Hence, when we are looking into the durability issues, we are not just interested in the strength, but we are also interested in to reduce the shrinkage cracks so that we do not create any permeability in the concrete for the ingress of water and moisture. Now, some special types of high performance concrete are described. See, the high performance concrete is a generic term which can be applicable for these following types of concrete. The first one is the high strength concrete with an upper limit of the cement content. The second is the self compacting concrete. The self compacting concrete is like a flowable concrete which does not need sufficient vibration. Now, the self compacting concrete is used when there is huge reinforcement, especially in seismic regions and where it is difficult for the concrete to flow. In that case, self compacting concrete can be used. The reactive powder concrete can give again very high strength concrete. The high volume fly ash concrete uses the industrial byproduct of fly ash. It has several advantages. First of all, it has reduced shrinkage cracks. Although it gains strength slowly, but over the time it may achieve high strength. And the fifth type of concrete is the fiber reinforced concrete. In this type of concrete, small fibers, either it can be carbon or graphite, or the more popular one is the steel fibers, which are poured into the concrete during its casting. The benefit of fiber reinforced concrete is that it reduces the shrinkage cracks, and since the fibers are oriented randomly, it can also be used for a region which is subjected to stress concentration and subjected to tensile stresses. In a post-tension member, the concrete next to the anchorage blocks is subjected to high stress concentration. The type of concrete at the end blocks may be different from that at the rest of the member. I told last time that the anchorage block actually bears against the concrete, and right next to the bearing plate, the concrete is subjected to a high stress concentration. This leads to some transverse forces which are called bursting forces, and these forces can create cracks within the concrete. Now, in order to reduce the chances of cracking in these end regions, a special type of concrete can be used only for the end regions and not throughout the member. Now, fiber reinforced concrete is an ideal form of concrete to use to check the cracking due to the bursting forces. And the following photo will show that the end blocks were cast separately with high strength concrete. In this photo, you can see that the end blocks were cast separately because these end blocks are subjected to high stress concentration, and hence a high strength concrete was used for the end blocks. But to make the member cost effective, the rest of the member is not made of the high strength concrete. Conventional concrete will be used for the rest of the member. And here you can also see the reinforcement and the layout of the tendons. And on the end blocks, you can see the bearing plates where the anchorage blocks will be attached. Next, we are moving on to the allowable stresses in concrete. In prestressed concrete design, as we mentioned earlier, that there are three important stages of loading. The first one is at transfer, that when the pre-stress is being transferred to the concrete, the member should be able to sustain those high stresses. The second stage is the intermediate stage, when a prestressed concrete member is transported from the casting site to its final location, then it is subjected to stresses. And third, in the final location, the prestressed concrete member is subjected to the loads during its service life. There is also another condition, which is the limit state, where the factored loads are used to calculate the demand within the concrete member. Now, out of this different load stages, the load stage at transfer and the load stage under service conditions are checked by the conventional elastic analysis. And in using this elastic analysis, some allowable stresses are specified by the code. It is similar to the earlier working stress design of reinforced concrete. IS 1343 specifies maximum compressive stresses for different grades of concrete under different loading conditions in section 22.8. Now, the following sketch shows the variation of maximum compressive stresses for the different grades of concrete under flexure at transfer. This sketch is used to calculate the maximum compressive stress under flexure at transfer. We have to remember this condition, that this is a compressive strength for flexure and these allowable stresses are applicable for the load stage at transfer. Now, for a post-tension member, the concrete grade can vary from M30 to M60 and the allowable stress varies from 0.54 FCI to 0.37 FCI. FCI is the cube strength at the time of transfer. That means before the prestress is transferred, samples of the concrete are tested, the strength is found out, and from that strength we calculate what is the allowable stress that the concrete can sustain due to the compression under flexure. Now, for pre-tension member, since the grade varies from M40 to M60, the allowable stress varies from 0.51 FCI to 0.44 FCI. Next, the code specifies maximum compressive stress for the different grades of concrete under flexure at service loads. So, there is no specific allowable stresses specified for the intermediate stresses, because for the intermediate loading is very case specific. Now, proper judgment has to be done to analyze a member for the intermediate loading. The code specifies only for the service loads. Now, for the compression under flexure due to service loads, the variation of the maximum compressive strength is given by the sketch. This is applicable both for pre-tensioned and post-tension members, that from M30 to M60, the allowable compressive stress varies from 0.41 FCK to 0.35 FCK, where FCK is the characteristic compressive strength of concrete. Now, the top curve is applicable in a region where the compressive stresses are not likely to increase during the service life. But if there is some region where the compressive stresses are likely to increase in the service life, then to consider this uncertainty, the code reduces the allowable stresses, which varies from 0.34 FCK for M30 grade of concrete to 0.27 FCK for M60 grade of concrete. Now, for direct compression, except in the parts immediately behind the anchorage, the maximum stress is calculated based on the maximum compressive stress under flexure. That is, the allowable maximum compressive stress under direct compression is taken as 80% of the maximum compressive stress under flexure. Now, the code also specifies some maximum flexural tensile stresses. Now, this is specified for the three different types of members that we had learned earlier. The type 1 member is the one where no tensile stress is allowed under service loads. Type 2 is a member where tensile stresses is allowed, but it is limited to 3 Newton per millimeter square. This value allowable stress can be increased to 4.5 Newton per millimeter square for temporary loads. For type 3 members, these members are also subjected to cracking under service loads, but the code specifies some hypothetical values of maximum flexural tensile stresses. See, this is an interesting point to observe. See, after the concrete cracks, the elastic analysis cannot be used in its exact sense, but the code allows us to use the elastic analysis for the service loads, so that the analysis procedure is simple and it specifies some hypothetical maximum tensile stresses in the members, which ensures that the cracking is not extensive in the type 3 members and the crack width will be limited. Now, in today's class, first we covered the constituents of concrete. We learned that the concrete itself is a composite material made up of coarse aggregates, fine aggregates, cement and water. There can be admixtures for the different types of situations. Now, the aggregates should be of good quality, that should be sound, the shape and texture should be good for a proper high strength concrete. It should not have any deleterious materials. Regarding the cement, the code allows us 4 types of cement, and the water also should be of good quality without any deleterious material. Potable water is acceptable for concrete, and these 3 constituents should be mixed properly and the concrete should be cast. There are admixtures which are allowed by the code. Next, we moved into the properties of hardened concrete. The first property we studied was the strength, which is the primary requirement in prestressed applications. For the strength, we studied 2 types of strength, the compressive strength and the tensile strength, and we found that the compressive strength is quantified by a number called the characteristic compressive strength, which is based on a probabilistic distribution of the results, and the tensile strength is measured by usually 2 types of tests. The flexural tensile strength and the splitting tensile strength are calculated from flexure tests and the cylinder tests, as I showed earlier. The tensile strength can also be calculated from direct tensile tests, but those are relatively difficult to perform. The second property that we studied was the stiffness of concrete. Now, the stiffness of concrete is quantified by the elastic modulus. We need this quantity when we calculate the deflection of materials. The calculation of deflections becomes important if the member is of smaller depth and longer span. Another very important criteria of hardened concrete is the durability. As a concrete structure ages, the cost of maintenance and repair can be substantial. In order to limit this cost, the durability issues are being emphasized at present. In IS 456-2000, there is a separate section on durability, which is quite comprehensive. It is expected that the pre-stressed code IS 1343 will also be revised to have a more enhanced section on durability. At present, the 1343 provides the durability requirements in the appendix. It specifies a minimum cement content and a maximum water to cement ratio depending on the exposure condition. The exposure conditions are defined as moderate, severe, extreme, Now, those definitions we are not covering here because those are already covered in IS 456, and then we studied the definition and the types of high performance concrete. As I said that at present high performance concrete is becoming more and more popular because we are able to quantify its properties. There can be different types of high performance concrete. Now, the main requirements of high performance concrete is that it should be of high strength, it should be durable, there should be minimum shrinkage cracks, it should be easy to cast, and it should be cost effective. Now, in a prestressed concrete member, different types of concrete can be used in the end blocks as compared to the rest of the member. The end blocks are subjected to stress concentration, and fiber reinforced concrete can be used in the end blocks to sustain those high stresses at the anchorage regions. Finally, we moved on to the allowable stresses in concrete. These values are needed in the analysis of prestressed concrete members at transfer and at surface. They can be also used for the analysis at intermediate loading stage with proper engineering judgment. We have found that the code has specified the allowable compressive strength for flexure at two conditions, one at transfer and one at service loads, and these allowable compressive stresses depends on the grade of concrete, and then the code also specifies the allowable tensile strength. Now, that is based on the type of member that we intend to design. The type 1 member, no tensile stress is allowed in the concrete. For type 2 member, the tensile stress is allowed whose value is 3 Newton per millimeter square, and it can be increased to 4 Newton per millimeter square for temporary loads. For type 3 members, these members are subjected to cracking. In that sense, elastic analysis is not truly applicable, but the code allows us to apply elastic analysis, and for that it specifies some hypothetical maximum tensile stresses. Now, this simplifies our calculations, and the hypothetical tensile stresses are such that it limits the amount of cracking and also it limits the amount of crack width. In our next class, we shall continue with the properties of hardened concrete. We shall see the stress strain curves of concrete, and then we shall study the two very important properties of concrete, which is the creep and shrinkage. These two properties are very important for prestressed concrete members. Thank you.